Hey everybody, and welcome back to Calc 3 Online. So the plan for today is just do some more examples related to these surface integrals. Last time I kind of just showed you the idea with them, which is really just that they're basically a 1D up version of a line integral. You're just looking at how much stuff sort of is above or below some sort of surface, or you can think inside or outside. Or you can think of it as that would be sort of a ds with respect to like surface area kind of surface integral. But you can also do a dot product kind of form of a surface integral, like a dot product line integral we could do. And there we're sort of curious about how much stuff passes through a surface. That's sort of and that's that thing flux that we're finding, okay? And that's like this one. So if I say evaluate the surface integral, f dot ds for that vector field right there, where S is this parallelogram defined by these parametric equations between these bounds. Basically what we're saying, and I'm not going to figure out exactly where the parallelogram is, but let's just say this is my parallelogram in space, okay? And what we're kind of curious about is how much stuff, I could plot this vector field over this, and we're sort of curious about the connection between, the vectors might move in all sorts of weird directions and stuff, but we're sort of interested in how much stuff moves through that, or like across the surface of that parallelogram. That's the idea. To do these things, we did one of these at the end in the last video, but they're kind of lengthy. And the idea is basically you have to find your R with respect to U, R with respect to V, you take a cross product of that, then you set up a dot product, and then at the end you still got to do a double integral. So quite a bit of work. Let's just get into it here. So R with respect to U, actually I think for the sake of space, I'm going to get rid of that. R with respect to U is just going to be 1, 1, 2. Right? R with respect to V is going to be 1, negative 1, 1. And so if you do R with respect to U cross R with respect to V, pretty nice cross product because it's all constants. You'll just get 3, 1, negative 2. Then you would have to do f of R with respect to U and V. So this is the idea where we're like combining that parametrization with my vector field, right? And all you got to do is, you have X, you just pop that in there. You have Y, you pop that in there. If you do all of that, you would get the following. So, this is coming up in here because when we do X times Y, you basically got the factors of a difference of squares. So I'm just writing it that way. But, so that is f of R of U and V. And then the idea is, right, you got to take the dot product of this with this. But this is where we have a little bit of choice. So there's two ways, right? Because we're talking about orientable surfaces, and just like I kind of had in that picture before, we can think of the parallelogram as having sort of like an upper direction, sort of like one that points up, or one that sort of points down, right? The normal vectors I'm talking about to the surface. And so we have choice here, and right now you can see because it's a negative z, it's basically going in like the downwards direction. We're kind of doing this one right now. And we might be curious with how much stuff passes through it that way. But we might also want the opposite direction. And if we wanted the opposite direction, then we just got to take the negative, right? Because this is going to give us one cross product or one normal vector, but there's another normal to that plane. And it's just the negative of all that. So I'm going to do it where you're curious in the upwards direction. And like the problem would probably just have to specify, but because technically there are like two choices there. But I'm going to dot product it with the minus of r with respect to u cross r with respect to v. That would be representing the upwards direction in this problem. If you wanted the down direction, then you can just do that based on the looking at the negative, or just taking this vector as is. Sorry. Okay, so if you do that dot product, you'll get the following. And if you look at this, you've got a minus 3 times 1 plus 2u plus v, blah, 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 and then a positive 3 times 1 plus 2u plus v, blah, blah, blah. So it's actually pretty nice because a lot of stuff cancels, and really the integrand for this double integral is actually just that. So it turns out to be not actually a very horrible double integral at all, even though it was looking like it could have been pretty messy. So in the end, your like u is going 0 to 1, your v is going 0 to 2, and then you're just doing 2 times u squared minus v squared du dv. And everything there is like a nice, polynomial integral. I'm not going to spend time to go through that. You would just get 4, okay? And what this basically means, you can think of, this is flux, this is what we just calculated, and you can think about it as basically a rate of flow. And the flow is pretty abstract. It can represent all sorts of different things. And the idea is basically there is a positive amount of stuff passing up through the parallelogram, okay? If we had gotten a negative, it would just mean there's more stuff going down through it because we were computing the change in the forward direction, and we got a positive number, so there is basically more stuff flowing, more stuff flows up through the parallelogram. Okay. That's about as weird as they probably get. I mean, you can definitely get like messier cross products and dot products and all sorts of stuff, and the computation can take longer, but that is the main idea of these problems. So I just wanted to take a second and kind of build up a formula of sorts for cases where your parametrization is what we would really call like a graph in math. So if you have a function like, say, x equals g of y of z, then you should just let y equal y and z equal z. That should basically be your parametrization, and then x is the function of y and z. And in that case, okay, if we just go through it, you would have y with respect to, r with respect to y, sorry. And that would be g with respect to y, and then 1 and 0. And then r with z would be, I don't know what I'm doing, dot colon, these are equal, is g with respect to z, and then 0 and a 1. And so if you do the cross product, you'll have gy, 1, 0, g, z, 0, 1, I, j, k. And if you do that out, you will just get 1 minus g with respect to y minus g with respect to z. And so what's nice is, there's, I guess one thing that's really, the main thing that's nice is that these are just going to be 1s and 0s. It makes a pretty easy cross product no matter what you have. And so if, f is going to basically be some sort of 3D like PQR thing, and those might be in here, functions of x and y, or x, y, and z, really. And all you got to do then to do this surface integral is if you dot product this thing with this thing, right, you would just get p minus q partial of g with respect to y minus r partial of g with respect to z dA. And that's sort of a handy, formula if you want to think about it to remember. It's nice because it saves you some time. You don't have to go through some of these kind of steps by, full brute force. If you just know this thing off the top of your head, you can go ahead and just whatever, if P is just YZ, you put in this case, because it's parameterized that way, you put in YZ and then so on and so on and so on. And this formula sort of changes depending on what this is, right? A lot of times we're used to Z as a function of X and Y. And, so here we would let X be X and Y be Y. If that was the case, then we get this formula, let's say again, for the flux situation here. And you can see it's pretty similar. Some stuff sort of shifts around. There's actually a pattern where there's a way to figure out the pattern. Like if you did y equals g of x and z, the third case that we didn't talk about here, you would see a very similar thing again, which isn't hard to believe. Basically, you're always getting partial derivatives that look sort of like this. So I wanted to show you why this can be a little quicker in an example right here. So if we want to find the flux across this field, or across, this surface with this field, then this object, right, can just be written as, so there's actually two surfaces here. So let me back up a second. And the upper one, right, is just z equals 1 minus x squared minus y squared. And the bottom is just the plane z equals 0, so just that disk down there. But both those are just nice where you can just write z equals something, right? And so you can just go and use this kind of formula instead of rather getting into parametrizations and all of that. You can just hop into this formula if you remember it. So if we were going to do that, notice P, so this is P, right? P is just Y, so in here I'm going to put minus Y. And then partial of G with respect to X, right? This is my function G. So I'm going to do it across, I'll have to do two surface integrals here, just to be clear. And so I'm doing this one first, then I'll add to it this one. That would just be minus 2x, right? And then just kind of moving through, q is x, so I got a minus x. Partial of g with respect to y is minus 2y. And then plus r is just z. And z, though, is 1 minus x squared minus y squared. So you don't want three variables in there. You want, the whole idea here is to have two, right? And then just dA, right? And you go ahead and simplify some of this. You can get 4xy, let's see, plus 1 minus x squared minus y squared dA. And now it's just back to a chapter 15 problem. And, because of the kind of structure you have here, the circular structure of a paraboloid, like an upside down paraboloid. Also, this is a big clue. You should just do polar. That would definitely be the nicest thing to do there. So if you just go and put everything in with polar, you would get this. I ran out of room there a little bit, but this is just 4xy, right, plus 1 minus r squared, and then I have my Jacobian RdRd theta in there for dA. And, we've got the full, based on this picture, right, you can see it's the full, it's a unit paraboloid in a sense, right? And so r is going 0 to 1, and then the full 2 pi is happening, right? So if you compute that out, you would get pi over 2. And so that is one of my surface integrals. That's basically computing the connection between the vector field and the S1 paraboloid surface, but now you have to do the other one. So now you have to do, so maybe I should label these. This one was the paraboloid, and now down here I'm going to do just like the, we'll just call it the, z equals 0 disk, basically. And, for the disk down here, for z equals 0, you can get the unit normal really easily. Like, you can just do n equals minus k, right? That is definitely a unit vector. And we want the, positive outer orientation. And so we would just take minus k as the unit normal in that case. So here we would get double integral f dot ds to really just equal, this is over like S2, to be just f dotted with minus k ds. And then, the I and j components have zeros there. So when we dot it, we really just need to look at the z. And so we just get double integral over S2 to really just be minus z. And then dA, right? But on that surface, S2, z is 0. So this is really just the double integral of 0 dA, right? Which doesn't add then anything to this problem. This just equals 0. And so to put it all together, basically the flux across the full surface S, like f dot ds, is just the pi over 2 plus the 0, so just pi over 2. So that is like the net change across this whole enclosed surface that you got going on in regards to that vector field, right? You get a different thing, of course, if you had a different vector field, but that is, I used to do these problems when I was pre-med. I would do some things where I would be computing the flux with regards to like cell membranes, and I could use flux to calculate how much stuff sort of leaves or enters a cell, for that matter. And so you can kind of use your imagination. There's lots of applications of these things out there, but that's just one of them. Speaking of applications, I just wanted to kind of show a few more really quick. So if any of you are in physics, I think you would have studied this, or at least in Physics C, you would have studied something called Gauss's law. And Gauss's law sounds something different and unique, but actually it's exactly what we're doing. It's just computing flux across a closed surface. They use different symbols. This is what they use for it, but you can see the structure is the same. E is just basically, I think it's E because it's like an electric field here. And they use dA there, but it's just like ds. It's the same thing. And it just exactly measures, again, how much stuff moves in and out, in a sense, of that field with regards to the object you got. And in terms of words, this is sort of what Gauss's law states, is it says that the electric flux through an arbitrary surface is proportional to the total charge enclosed by the surface. And so we're sort of checking, because flow rates can be like all sorts of things, so it can definitely be like electric fields. And so we're sort of just checking the correspondence between the surface and the electric field. And we just check that with the dot product, and by doing a double integral, over that thing, we really are checking like the net effect over the entire closed object that we have. This is used oftentimes in heat flow problems. So we could measure heat flux. So you can kind of think of, there's all sorts of application problems out there where you want to measure how the heat transfers through some sort of membrane. And so you can represent like new thermal technologies with sort of functional names, and like f of x, y, I'm saying, and then you can measure the flux, the heat flux across it. That's another one. You can actually use this to find the center of a mass of an object, which is kind of neat. There's some problems in the book about that. You can read them if you want. In general, they're just used to find the flow rate of pretty much anything. And flow is a very arbitrary term that applies to tons of things. Space-time has a certain flow to it. And I used Flux on these like higher dimensional kind of cosmology-related problems at one point. And it shows up literally all over the place. There's tons of things in the real world where we want to measure how some thing, whether it's an electric field or heat or something, reacts to some sort of surface. And whenever you're doing that, you're running into like a flux situation, okay? So there's a lot to do there, and in a flux problem, I mean, there's like a lot of calculations to do. This one was already quite a bit quicker because we have this kind of shortcut, but, a lot of times you have to go through all of this, and I just wrote down the integral, right, and a lot of times the integral could be really hard. Luckily, we're building actually up to a point where there's going to be a shortcut, and there's going to be something that is called the Divergence Theorem, and the Divergence Theorem is actually the last thing that we'll learn about in this whole course, and it's going to be something that will really, really help speed up computations of surface integrals.